Hello everyone and welcome to lecture 2.6. In this lecture we're going to introduce cuda C unified memory. The objective of this lecture is to learn the basic API functions in cuda host code for cuda unified memory. In particular, this means unified memory allocation and data transfer. cuda unified memory is a single address space accessible both from the host and from the device. This means that a pointer created in the unified memory address space can be used in device and host code without worrying about explicit data transfers. This is possible thanks to a specialized unified memory driver and in some devices a specialized hardware unit which manages consistency between host and device memory. Here we have the same partial overview of cuda memories of lecture 2.2 with addition of where unified memory fits in this overview. As you may remember, in device code, you can write it to registers, shared memory, and global memory in the GPU. Now, with the unified memory, you can read and write from host and device code to the unified memory address space without worrying of where the data is located. To allocate memory using unified memory, you need to use cuda managed. Its parameters are the same as cuda The only difference is that the pointer return in the first parameter now contains a unified memory address. Also, you always need to remember that the size of the array is given in bytes. There's also a third optional parameter indicating if you want the unified memory region to be accessible from any device or stream, with the default behavior for this flag being to allow access to any device or a stream. To free a unified memory pointer, you can use cuda free as with normal global memory, passing to the function the pointer to free. Even though with unified memory, the driver handles memory transfers between the host and the device, you also may want to copy chunks of memory between different regions. That is why cuda copy also works with the unified memory. For example, let's say you have a compute kernel which needs a temporal array filled with the input data. You can use cuda copy to copy data from the original input to the temp array. It's important to mention that the source and destination pointer can be any type of memory. For example, you can copy global memory addresses to unified memory region or vice versa. Since unified memory is accessible both from the host and the device, you may want to specify the transfer type other than cuda copy default to tell the driver from where or to where to copy the memory. For example, if the source is a unified memory address and you are copying to global memory, you may want that cuda copy access if possible the data from the device in order to avoid accessing it from the host and incurring a PCIe transaction. In this slide, you can observe the same example from lecture 2.2, but using unified memory. As you may have noticed already, there are no cuda copy calls from or to the device, demonstrating how unified memory simplifies code writing for the programmer. It's important for you to know that different compute capabilities have different unified memory capabilities. For example, prior to compute capability 6, there is no specialized hardware units to improve unified memory efficiency. Every time the drivers need to migrate data, the full memory blocks need to be copied synchronously by the driver, and there is no memory oversubscription. From compute capability 6 and onwards, there are specialized hardware units managing page faulting. Data is migrated on demand, and there exists the possibility to oversubscribe memory, enabling larger arrays than the device memory size. This concludes Model 2.6. Thank you.